Okay, so we're going to start with a simple system in which we imagine a cell. The anode's full and has 1 mole of electrons. The cathode is empty. It has some empty electrolyte. If we have the external potential, what is the definition of the cell? Well, the definition of the cell comes from the Nernst equation. So if we know what the cell potential is, that's the standard cell potential, which comes from the difference between the reduction and oxidation potentials. And let's say it's about around 1 volt, just for the sake of picking something up. We got the gas constant, we've got the temperature, we've got Z, so we're saying it's a single electron transfer. We've got the Faraday constant, natural log of the activities. So if we have that, then at some other time, we can say, well, if some of the charge is flowed, what is the cell and potential? And that changes, assuming that we again keep the resistance constant. And in both cases, we can determine the current for that particular configuration. Okay, so what we found works is using the concentration in the anode and cathode as approximations for the activity. That is approximate because we know that the volumes of the cathode and electrode change. We also know that we have inhomogeneous distribution of metal atoms in those. But for now, what we can do is we'll just treat them as though they are uniform and constant volume. So then coming over here, if we have a good expression for this, we should be able to determine for a constant resistance the current as a function of anode occupancy, Na, and it should go and drop. As we increase the resistance, that should decrease. This still drops off the same Na equal to 0. That will also give us a V cell versus Na, and that should be independent of the current, right? And just depend on the occupancy. The current versus the time should exhibit this as we increase the resistance, meaning basically as we increase the resistance, the rate of discharge gets slower. And subsequently, the V cell should also change with time. And we have some time where it dies out. Now, if we have these and we make our model, we should be able to model the concentration of electrons in the anode and cathode. Sorry, that's anode, that's is that right, anode? Let me think about that. Which one's the anode? Anode is good. Anode, yeah. Over time, we are pumping electrons out of it. Yeah, so that's cathode. C-A-T-H. So, over time, the anode, we're going to take electrons out very slowly due to current being transferred, and then whenever we have a metal atom convert to an ion, it's going to hop back up. So we have these jumps. At the same time, in the cathode, we have electrolyte ions that go in and they hop into the cathode, and when that happens, we have these discrete events. And at the end of the day, when we run out of metal to transfer, they go to 0, and that corresponds to that time there. Now, looking at the metal concentration in the anode and cathode, we should also be able to represent this and say that in the anode, we start out with a bunch of metal and goes and comes down, and it's slowly going to taper down as the voltage tapers off. The cathode is going to have a little bit slower uptake, but it'll also have this similar shaped curve. The concentration of the ions in the electrolyte will start out constant because we've maintained electrostatics, but as things come in and out, they're going to see a lot more variation, and then as we run out of juice, as time passes, that's going to go to constant again as well. So these curves are what we expect physically from a continuum model and what we should be able to get from our hopping model. So our hopping model is going to look like this. Basically, if we have a system like this, we got anode, electrode, electrolyte, cathode, and we have a set of charges, and this is a one-dimensional model, so some x with spacing delta x. Let's say we start by just putting some charges in. So we have some minus a plus b minus c plus d. And we know the center of these is delta x over 2, 3 delta x over 2, 5 delta x over 2, dot, dot, dot. Well, if we ask ourselves, what is the potential? We can have this potential due to the electrostatics that says the electrostatics at, say, delta x 5 over 2 is going to be equal to minus a delta x plus b delta x minus c 2 delta x plus d 3 over 3 delta x. Great. And that tells us about the electrostatics, but it doesn't tell us about what's happening due to this built-in charge. And that built-in charge from the Nernst equation is essentially giving us also a concentration gradient like this, which I'm going to call this VGR, the gradient. Now, that gradient is going to have a high and a low, and the delta is going to be V cell. And basically then, if we want to know the electrostatic potential here at delta x5 over 2, we need V electrostatic, delta x5 over 2, and we need VGR, delta x5 over 2, which is read from this curve. We're saying that the gradient is constant in the anode and constant in the cathode, but that it changes in the electrolyte. Okay, now we're going to set, for at least temporarily, we're thinking of setting the 0 to be the, for the gradient as the potential in the cathode, and that's great. The problem is that we can no longer use VGR and VES on equal footing, right? Because VES uses vacuum as the 0, and VGR is using the cathode. That's not a problem. And the reason it's not a problem is because in our calculation, we're never going to get the absolute energy. We're only going to get the change in energy, because we're talking about this metropolis algorithm in which we make a change, and we say, does the change happen or does it not happen? Right? And we know then the energy based on the potential and the charge at every point. So let's go through the algorithm that we're going to use. So we started at some t equals t0. Say, okay, great. So then we pick any atom or ion in the system, and we pick a random number, and if it's, we flip a coin, right? It either hops left or it hops right, if it's based on what the random number is. Now, if that site happens to be blocked, well, that means nothing can happen, which means we loop back up to the top, and we increment time. Oh, we also have to increment charge. Let's fix that. Loop, and current, etc. So when we loop back up, we have to increment the current and other things in the system, but we basically go up and we start over again. Now, if it's not blocked, then we look at what the change in the energy is as a function of the two configurations, right? And that is simply this sum of the potential times the charge at a site over all charges minus that for system 1. If that change in energy is less than or equal to 0, then we say it spontaneously hops. Now, if it's greater than 0, then it may or may not hop, depending on whether or not it satisfies the Boltzmann equation. So we pick another random number, and this random number, if it's greater than an exponential of negative delta E over KT, then we hop, otherwise it doesn't hop. And at the end of that, then we have to increment the system. We have to increment the current, saying some amount of charge has passed from the cathode to the anode, or is the anode to the cathode? Well, we have to figure out the direction on that. And then we also have to increment V cell and then the activities of the anode and cathode based on the concentrations. And that's just looking at the distribution of atoms, and then using the Nernst equation. And then we have T incremented from T0 to T0 plus delta T. And that's how we are going to increment the system as a function of time. The system evolves. This V cell here is coming from the Nernst equation. So as ions move, the potential changes, and that change in the potential will then impact the delta E and the rate that these things are occurring. Another open question is here is like, why is it if I have this system that it doesn't spontaneously discharge? Because it looks like it should, and the way it's written it should. The reason it doesn't is that if we start out, we're actually going to have our metal atoms sitting in the anode. We have a metal ion or two sitting in the electrolyte, and we have a metal atom in the cathode. And then we have background charges. In the anode, we have a positive background charge, I'm calling plus A. In the cathode, we have a negative electron charge, I'm calling C. And in the electrolyte, we have an E. Now, this plus A and minus C are due to small charges that are transferred from the cathode to the anode, or anode to the, again, there's some sign here we have to make sure we get right, but it's being transferred just due to the current through the external potential for some time. That's part of it, but the other part is that when there's an ionization event, there's a big change in charge. So for example, here, if we go from this structure to this structure, well, when this hops here to here, this becomes charge plus Q. When that becomes charge plus Q, that means that the background charge of the anode now has to change to A prime, which is equal to the original A minus Q over 3, because that charge is being distributed over the anode. And that's going to be relatively large. When we have say zero current flowing, there are going to be statistical fluctuations, a very small number of them, in which we have either metals hopping into electrolytes or electrolyte ions hopping into the cathode, but that's going to be immediately countered, and in the next hop, it'll probably hop or potentially hop backwards due to electrostatics. Now, talking about this negative E charge, that negative E charge is just the background charge needed to maintain neutrality of the electrolyte. So that comes about from our understanding of the composition of the electrolyte. And then the Q on our ion, that is just the charge on the ion, so it's just going to be plus 1 electron. And again, that's why these electrostatics are going to play such a significant role. Now, something also that's interesting and worth noting is that let's say we have a system, I made a very small anode and a small cathode, but gets electrolyte. Well, due to the gradient, there's going to be a tendency for those ions to bunch up at the cathode. And that's certainly makes sense. But the thing about our model is that because we have this background charge, we're going to have some electrostatics which oppose the migration, right? Because on one hand, we'd really like to see these Qs move down the potential gradient, but when we do that, we're going to leave this background charge unshielded, and that's going to want to have positive ions migrate to cover that up. And also these positive ions are going to have repulsive interactions with each other. So this is the model overall, and I'll shoot the board one more time so we can keep this on record. This is our Nernst equation, kind of our beginning simple thought experiment of what we're going to have. And we should be able to show what happens with a constant external resistance. And if we do have a constant external resistance, then we should get plots that look like this. For a constant R, we should get current and voltage as a function of anode composition or anode concentration. As a function of time over here, we should get current and potential. And then those we should be able to also relate to the concentrations in the electrodes, the concentration of metal, and the concentration of ions in the electrolyte. And that's basically talking about the time to emptying and the time for the concentrations. Over here, we've summarized our algorithm. And again, there's some sign errors here, sign issues here. We really need to make sure we get that correct. But the basic model is that we're going to have potentials. There's going to be two potentials. There's going to be an electrostatic potential, and there's going to be a gradient potential. The electrostatic potential is just due to the sum of the positive and negative charges. The gradient potential comes from the potential of the cell, which is coming from the Nernst equation, and the concentration of metal in the anode and cathode. Those electrostatic potentials, simple as they're expressed here, are actually a little bit more complicated, and we have this continuous distribution of background charge, and that background charge is what allows us to maintain charge neutrality of the electrolyte, and is what allows us to talk about ions hopping in and out, usually forward and backward, into the electrolyte and out of the electrolyte with open circuit, because that should happen. And then these electrostatics will also keep a charge balance in the electrolyte and in the system on the whole. So that is our model.